Then let's talk about query processing. Overview. So I sort of showed this slide before, and let's try to understand what's really happening inside a database system. So we have tables that are defined, and in this example, we assume that there are already some records that are inserted. And given those tables, the users can submit queries. Like here, I want to find basically where Einstein's office is located. So again, what you can see is that there are two tables, the instructor table and the department table. And information about Einstein is stored in the instructor table. However, this table does not include information about the building. So what needs to be needed is we want to combine data from instructor table and department table. So Einstein is affiliated with the physics department, and the physics department is located in the Watson building. So by combining these two tables, we'll be able to get the information. And given some SQL statement submitted by user like this, the database system translates this into a relational algebraic expression. So from SQL to relational algebra, okay? So what it means is, yeah, there are two tables, instructor and department, and we want to combine the data using the join operation. And then after the join operation, we are going to have one single intermediate table, and it may have multiple records. And among those records, we are interested in the record whose name is Einstein. So we are going to get a record with multiple columns. How many columns are we going to have in this case? I believe we are going to have 6 columns because there are 4 columns in the left table, 3 columns in the right table, total of 7 columns, but the department name is a common column, and in the output of the natural join, each common column will appear only once. So department name showing only once, so there will be 6 columns, and we are interested in only one column, that is building. So after the join, we have multiple records, but we pick the record having Einstein, and among 7 columns, we are going to pick only one column. And as a result, the outcome will be building and Watson. So that's what you're going to get. One problem that you can see is that at the end of this join operation, we are going to have many records, and we don't really need such many records, right? For that reason, the system will try to do something smarter. And that is basically something like this. We know that we are interested in Einstein. Therefore, from the instructor table, we may begin with selecting the record having Einstein as the name. And given this only one single record, we are going to find the relevant records from the department table. Basically, it's just like this. From the instructor table, we get the record having Einstein, and we know that the department name is physics. Therefore, we look for the record in the department table having physics as the department name, and we just put those records together, and then we output the building. So let me say that this is the expression 1 and this is the expression 2. And we know that expression 2 will be a lot better and at a very high level. Why? Because we select the relevant records as early as possible. So from here, when you are moving from expression 1 to expression 2, you will be doing early selection, okay? So here you had a late selection, but you turned this into an early selection, And in that way, things will be getting faster. So such a thing is called an execution plan. The reason is this is essentially an algebraic, relational algebraic expression, but you are going to add some more information. So today, we are going to learn different algorithms for this selection operation, different algorithms for this join operation, and so forth. So we will also specify what exact algorithm, specifically what algorithm we are going to use for each operation. So for selection, we are going to use this algorithm. For this join, we are going to use that algorithm, and so forth. So we are going to annotate the relational algebraic expression with more details, including the algorithm to use. And such a thing is called the execution plan. So we have a complete plan as to how we can get the wanted result like this. So given this detailed execution plan, we actually create some processing, so we actually create the operators, and then we started running those operators using the algorithms that we are going to cover today. And those operators collectively will produce the result that we are looking for. So this is the whole pipeline that the database system will go through to begin with the SQL statement written by user, and then the final outcome, which is a table containing all of the records specified in the SQL statement. So this is an overview. And we will focus on those things. Like query processing will be related to this, and the last part where, so there is something called evaluation engine, and this engine will create operators and run those operators. So we are going to learn such details today. Do you guys have any question at this point? If no question, then please type N. Okay, I want to get some confirmation from you guys. Okay, thank you very much. So I covered those things like parsing, evaluation, equivalent expressions, yeah, something like that. So we will also learn those like equivalence rules when we are learning query optimization. And I talked about query execution evaluation plan. Oh, I forgot to upload those slides. I will upload them right after this class. So in this chapter, and I believe that is, what is the chapter number? I think that is a chapter 15 in the textbook. So in this chapter, you essentially need to understand two things, okay? Number one, you need to understand how each algorithm works, okay? How each like join algorithm works, how each selection algorithm works, how each sorting algorithm works. So first, we will learn multiple algorithms, and you need to know how, you need to understand how each algorithm works. And then for each algorithm, you need to be able to estimate the time, okay? How long it will take to do each operation. So if there is a join algorithm 1, then how long it will take. That's what we need to know. And the assumption here is a computer system has a lot of components, including the main memory, nowadays the flash drives, the hard drives, and networking interface, and so forth. However, here we assume that the performance of bottleneck in that hardware system is the disk, because the main memory is very fast, okay? The main memory has the speed of like 10 gigabytes per second. The main memory is very fast. However, hard drives, about 100 megabytes per second or 200 megabytes per second. Okay, that's the conventional like magnetic hard drive's speed. Okay, so you can see that hard drives are noticeably slower than the main memory, but you also need to keep in mind that that is the maximum speed. The reason is whenever you do a disk seek, then you are going to use like about 10 milliseconds of time to move the disk head from here to there. Okay, so you can do about 100 disk seeks per second. So in the worst case, if you really read like 1 byte at a time per disk seek, then you will end up with 100 bytes per second, considering the data that you actually need. So it can be the speed, the actual speed of the hard drive can be anywhere between 100 bytes per second and 100 megabytes per second, depending on how many disk seeks we are going to have. Okay, so you can see that the hard drive is much slower than the main memory. So when you are estimating the cost, you will focus on two important operations on the disk. Block transfers. How many blocks are we going to read or update? And how many disk seeks we are going to have, okay? And in general, we will have some parameter values like, oh yeah, like 1 disk seek will take about 4 milliseconds, or as I roughly mentioned, like 10 milliseconds. So that is the specification of the hardware that you use. But magnetic hard drives will have some disk seek delay, okay? Like anywhere between 5 milliseconds and 10 milliseconds. And then when you know the number of blocks that you are going to read or update, then per disk block, there will be some cost. So here, whenever you read 1 disk block or update 1 disk block, then it will take 0.1 milliseconds. So roughly speaking, I said that if you are reading blocks consecutively, then the bandwidth is like 100 megabytes per second, okay? Fast ones are about 200 megabytes per second. So let's assume that 200 megabytes per second. And each block is about 4 kilobytes. So 4 kilobytes divided by 100 megabytes per second. And if you do the math, then you are going to find that, oh yeah, let's assume that this is 200 megabytes per second. Then you are going to get that, oh yeah, then it is about 0.2 millisecond. So that's what you're going to get, okay? So how can we get those values? You can start from the bandwidth of the hard drive, okay? So at a very high level, you need to understand each algorithm. If you don't understand the algorithm, then you cannot estimate the cost. Number 2, cost estimation. So given the data that is provided and given an algorithm that the system picked, how long it will take, and how can we do this based on the number of block transfers and the number of disk seeks, because we know the per block transfer cost, which is 0.1 millisecond or something else, and per seek cost, which is about 4 milliseconds or like 10 milliseconds, depending on the drive that you use, okay? So understand each algorithm and possess the ability to estimate the cost. So you will later see that the slides will contain some formulas, okay, about in this algorithm, given this setting, here's the number of block transfers and here's the number of disk seeks. So there will be formulas. My recommendation for you guys is when you are taking the final exam or when you are working on homework assignment 3, which needs to be posted soon, yeah, you can use those formulas, but what's the value? If you don't really understand those formulas and you just barely use them, then you don't get much out of it, okay? So I would recommend you to not memorize the formulas and then rather try to understand why those formulas are formed that way. Or you may like just to try to solve the problem without using formulas. Because if you truly understand the algorithm, then it is always possible to estimate the number of block transfers and the number of disk seeks. So my recommendation is not to memorize those formulas, or before you memorize those formulas, please understand why. Secondly, if you just merely use those formulas, then actually you may not be able to answer homework questions or final exam questions correctly, because those formulas are derived under certain assumptions. And in the questions that I post, those assumptions may not hold. So if you need to estimate the cost under different assumptions, then you cannot use those formulas, okay? So that is one thing that you need to be careful about. You need to understand the algorithm and understand the situation, and you should possess the ability to derive the cost, okay? So don't plug in numbers into formulas without understanding those algorithms. And in the long run, I believe this is very important, because if you want to be a software architect or a software engineer who wants to build some innovative software systems in the future, then this is what you need to do. At a very high level, you want to convince why customers need to use your system rather than others, because it's fastest or it's faster than all others, and you need to justify why. And when it comes to that argument, the business is essentially what are the key operations that are necessary, how expensive these operations are, like time-wise, and how many times are you going to run those operations. So those things are necessary to convince the customers or like investors as to why your solution will be the best, why it'll be the fastest. So I think that what is truly important is to possess the ability to estimate the cost. And also, I mean, understanding algorithms and inventing your own algorithms when necessary. So I want you guys to achieve all of those things, okay, throughout this chapter. All right, so please keep in mind that what we care about is, because the hard drive is a bottleneck, you need to know how many blocks we need to read or write, and how many seeks, right? How many times we are going to move the disk ahead, okay, during the course of an algorithm. So when it comes to selection, there are a bunch of things that are mentioned in the slides. So it is more like when you have a relation R having many records and many columns, selection has one input, which is the relation, and predicate P, which is a Boolean expression that will be evaluated for every record, okay? So it's like P can be ID equals 1, 2, 3, 4, or height equals 6, or weight is anywhere between like 190 pounds and 210 pounds, something like that. So the predicates are Boolean expressions, and they may be connected with or and. So or means like disjunctive, disjunctive expression, Boolean expression, and when you have and, then it's a conjunctive. But these are the kind of predicates. So the predicate, so it is relatively simple in the sense that it's a unary operator having only one input table, but you may have a variety of Boolean expressions in the predicate. At a very high level, there are two approaches. If you go over the slides after the lecture, there are lots of details, but at a very high level, two approaches. Number one, you just read everything from the beginning to the end, linear scan or linear search. So you read every record. If there is like 1 terabyte of data in this relation R, then you need to read 1 terabyte of data, right? From the beginning to the end. And for each record that you read, you evaluate the predicate, like, oh, is the ID 1, 2, 3, 4? Is the height 6? Or is the weight anywhere between 190 pounds and 210 pounds? Something like that. So that is the linear search. The other one is when you have a table, and in most cases, when you have the primary key, which is the ID, typically, then you are going to have a B plus tree built for the primary key. So for the query select ID equals 1, 2, 3, 4, then by using the B plus tree with the logarithm overhead, you will know which record will have this ID 1, 2, 3, 4. So let's just say this is the record having ID of 1, 2, 3, 4, and let's just say it is located at 1000K in the file system. Then by using this B plus tree with the search key being 1, 2, 3, 4, you will do the search, and then you will hit a leaf node, and the leaf node will essentially have an entry saying 1, 2, 3, 4, which is the key, and the location where this record is stored in the file system, like 100K, okay? So by using this pointer, which is the location information of the record, you can access the record directly, okay? So once you finish the search using the B plus tree, then you know where the wanted record is located. So at a very high level, how we do selection, you scan everything, in particular if there is no index, okay? If there is no index, then you scan everything. It will take a very long time, okay? But if there is an index, particularly if the query involves the primary key, then yeah, you can do the search very, very quickly, okay? So it's one or the other, scanning everything, or if there's an index, then you use this, okay? Is this clear? If clear, please type Y. Okay. So let's try to understand a little more details. So let's think about some query like this one. So selection where ID is greater than 5, 6, 7, 8, and relation R, okay? Then let's just say you have this relation R with ID, and there might be ID 1, 2, 3, 4, and many, many IDs, and after this you may have ID 5, 6, 7, 8. And you have the B plus tree. And you are interested in finding all of the records whose ID is 5, 6, 7, 8, or bigger, meaning that in terms of lexicographic ordering, IDs that will be after 5, 6, 7, 8. So what it means is that when you have the B plus tree, let's just say the smallest key is 1, 2, 3, 4. And there'll be many, many leaf nodes in general. And by doing the search, you are going to hit a node having 5, 6, 7, 8. And as you remember, in P++ tree, in a P++ tree, all of the leaf nodes are linked. So it is designed to support range queries. So how we can do support such a query? You just like do the search in the P++ tree, and then you're going to hit a leaf node. Then you will keep following pointers at the leaf level, and you are going to access all of the keys that are 5, 6, 7, 8, or after 5, 6, 7, 8 in lexicographic ordering. And all of those leaf nodes will have pointers to the relevant records, okay? So by using these pointers, you'll be able to access all of the records satisfying this condition. If there is no P+ tree that can be used because there is no tree constructed, then you need to do linear scan. You need to read everything from the beginning to the end. Okay, is this clear? So at a very high level, range queries can be supported. Now let's go one step further. How can we support conjunction? Okay, so let's think about this. There are many ways, but let's think about this example. Okay, so how about that? Selection, name equals John, and, okay? So this symbol means like logical and, right? Name equals John, and CT equals Albany, where the input relation is a student. So we are interested in finding all of the students whose name is John and whose city is Albany, okay? And if there is an index built for John, okay, then we can use it, okay? So in this case, using the P+ tree, we will find all of the Johns quickly. And then for all of those Johns, we will do additional checking, okay? So you first find all of the Johns using the index. And then in particular, if there is no index for the city, then you need to additionally evaluate this condition for all of the Johns that you found. If there is an index for city as well, then one possibility is you may still decide not to use this index at all, because you can anyway get a very good, like, small set of record whose name is John. So you may decide not to use the index for city. However, if you decide to use a city, then what you can do is there is a set of records having John as the name, and there will be another set of records having Albany as the city. And you need to get the intersection between these two sets of records. So conceptually, you may have to do set intersection, okay? So at a very high level, there are many different ways of handling logical AND or conjunctive Boolean expressions or predicates. I just mentioned that there are several ways, and we may decide to use indices, or we may decide not to use indices. If I provide two more details, I'm not sure if any of you guys have some curiosity of this kind. Is it possible to build an index for names? So I didn't talk about a lot of details, but I kind of talked about keys like indices for names and IDs. And your question might be that, oh, what if there are multiple records with the same name? And we didn't cover those cases using when we are studying P plus trees, right? And at a very high level, it is possible to handle multiple records with the same key, like same name. And similarly, it is possible to it is possible to build an index for the city column. Although there are many people living in Albany, it is still possible to build an index. And there are multiple ways. One easy solution is the algorithm that we learned in class are designed to work well when when each key is unique. Okay, when there are no duplicate keys. So in reality, let's just say there are two records, R1 and R2, and both of them having John, okay? And let's just say this is located at location 1000. And let's say the second record, R2, is located at 2000. So one way to handle this case is, although logically the key is John only, you just combine the key and the actual location of the record, like 1000. You just put them together and use this as the key. Then you can see that I just made the keys unique, although their original keys are not unique, right? There are two records with the same John. However, we concatenate the actual locations of those records on disk, okay? And by adding such suffixes, I just differentiated these two keys, so they are no more identical because of the suffixes that are added. And each record will occupy a different location on disk. They cannot have the same location, right? So this is one way, and there are other ways. So one thing is, yeah, it is possible to use the P plus tree for many records with the same key. That is still possible. Number two, when you decide to use indices, so there might be one index for name and another index for city, and sometimes it might be better to use just one index rather than two indices. And in particular, I would probably use name only. The reason is, I don't know. Let's just say the name is not John. Let's just say there is a name that is like fairly unique. I don't know. I mean, let me use my name. Full name, okay? And I don't know, I mean, how many people in the Albany area will have the same first name as me? Probably very few. Let's just say at most 5 or even 1. Then this selection will be highly selective in the sense that you may have like millions of records, but only a few records will satisfy this condition. So this condition, this predicate is highly selective. Whereas, on the other hand, this predicate that involves a city being Albany is not selective. There may be like 1 million records satisfying this condition. So if you decide to use this condition, then you will end up with retrieving so many records. And that is not going to be good. So what I would do is I decide not to use this index for city because it's not selective. And in particular, if the name is my name, then it's going to be selective. So I use that index for name and I retrieve a couple of records. And then for each record, I check the city is Albany, okay? So this is called like selectivity, and we can do some selectivity based like optimization as well, okay? So I kind of talked about some details, and I'm gonna wrap up our conversation about selection, essentially filtering out records. At a very high level, there are two approaches. You do linear scan. You read everything from the beginning to the end, okay? 1 terabyte, then it's going to take a fairly long time, like 1 hour, okay? if you have an index, you use this, and range queries can even be supported because P plus tree is an ordered index. Any question? If there is no question, then let's talk about sorting. This is very, very important, and probably I'm still like hesitating between the programming assignment programming assignment 2. But I may like want to do some survey. Last time I did some survey and then I measured the interest in P plus tree. But after covering this sorting algorithm today, I may conduct a poll survey like early next week, Tuesday next week, and let's just see. If there is way more like interest in sorting, then I may decide to do sorting instead of P plus tree, or I may allow both options. So let's just think about it. Sorting is extremely, extremely important. It's very, very useful in computer science. And when you are learning, when we cover the join algorithm, so you will also learn that sorting is very, very useful. One important aspect is, in the case of SQL, select blah, 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 and then you have like order by. Because you want to like sort records because it may more sense. So for example, I may be interested in seeing certain people based on their like ESSA levels from the richest to the other. So yeah, I mean, we want to sort records in many cases, okay? In addition to that, sorting will make problems easier, okay? In the case of join, in the case of aggregation, you will find that sorting is one important approach that you may use to make the problem easier. So when you are seeing a hard problem, one thing that you can do from the perspective problem solving is to make the problem easier, okay? So as an example, let's just think about like duplicate elimination or distinct counting. You want to come up with a distinct count and or like eliminate duplicates. They're kind of very related questions. And one thing that you can do is, I mean, there are many ways to do this, but you just assume that the numbers are sorted in advance, like that. Then you can see that eliminating duplicates is much easier when the numbers are sorted because all occurrences of the same number will appear consecutively. So you are seeing one for the first time, and if you see one again, then you can discard this. And you are seeing a larger number, which means it's the first occurrence of 2, first occurrence of 3, and so forth. So you can see that sorting the raw data in many cases will make the problem much easier. So this is something that you should remember, okay? When you are solving some data management problems. How about sorting the records? Then you may find that this is very easy. The problem becomes easier. And I'm not sure if you are interested in some recent like data storage approaches or indexing techniques that are adopted by like HBase and like Cassandra, which is made by Amazon a while ago. So when not Amazon, but it's motivated by Amazon. So when you are interested in like such recent storage or indexing mechanisms, they also extensively use sorting. Okay. So first of all, I'm trying to emphasize the importance of sorting. And let's just say you guys agree that sorting is going to be very useful. Then the next question is, how can we do sorting? And you learned some sorting algorithms, maybe starting from like bubble sort, like quick sort, merge sort, like radix sort, I'm sure you learned many interesting and important sorting algorithms when you started taking some introductory computer science courses. So they are useful, but in the context of database systems, we are considering the case where the data is too large to fit into the main memory. Okay, so you cannot use a quick sort. So for example, Java supports many sorting functions. So if you look at, I forgot the name, the exact like package, but if you are, for example, using the arrays class, then there is some like sorting function provided. And I think here and there will be a lot of like sorting functions that are provided by Java, but they are all memory based. The problem is the data is too large to fit into the main memory, so we cannot really use those existing sorting functions. So on one possible programming assignment option is implement the following external sorting technique. Therefore, you are going to have your own library, which is not limited to the size of the main memory. You can sort 1 terabyte of data, although your laptop machine has just 10 gigabytes of memory. You can still sort it, okay? By using like Java's sort function, sort method, but also in conjunction with your implementation. So at a very high level, the idea of external sorting is to sort the data using the disk because we cannot put all the data in the main memory. Too much data to fit into the main memory. And here is the idea of external sorting. Let's just say you have one single file having many records, but this is a like way simplified example where you have a total of 12 records. Okay, it's simplified, okay, like drastically simplified. But in practice, yeah, you are going to worry about like billions of records or tens of or hundreds of millions of records and so forth. First, what you do is you sequentially read the records in the file and keep loading them into the main memory or some reserved area in the main memory. So your memory may be 2 gigabytes in size, and you may decide to use just 1 gigabyte for the sorting purposes. And sometimes we can call this a buffer, okay? Some area in the main memory that is reserved for some specific purpose. So let's say we decide to use 1 gigabyte to sort the records. So you keep reading the data and then loading them into this buffer. And at some point, the buffer will be full, right? And in this case, yeah, if it is full, so you decide to save this on the disk. And we call this a run, okay? It's a special term that is used. Let's just say this is run 0, okay? So you read the data as much as you can, the memory is full, so you sort the records in the main memory and then you save them into file, and then you empty the buffer, you clear this up. And then you move on to the next location in the file, and then you keep reading the data. And once the buffer is full, then you save them into a new file. So this is run 1. And you repeat this process. And in this example, you end up with creating 4 runs, okay? 4 runs. So run 0, run 1, run 2, run. Oh yeah, I'm sorry. It needs to be like run 3, not run 4. Okay. So are you guys okay up to this point? So if there is no question, so that's what we do in the first phase or first pass, and we create like runs. Okay, run creation. That's what we do. And then what we do is we decide to merge multiple runs into one run. So here we are merging two runs into one run, and let me name this like run 0 prime and run 1 prime. So these two runs, R0 and R1, are merged into one single run. R0 prime and R2 and R3 are merged into one run, which is R1 prime. And then R0 prime and R1 prime are merged into another run, and that's sorted, so it's done. Okay, so it's exactly what I used to do when I like create like midterm exams and final exams before the pandemic. So I have like in some cases like 100 blue books, and I pick like 5 of them and I sort them based on the student ID or the last name. Okay, so I have one batch of 5 sorted blue books, another batch of 5 sorted blue books, and then I keep merging them. And merging is fairly easy because just assume that this is like a deck of cards, right, that are sorted. So you have one sorted deck of cards and another sorted deck of cards, and you want to merge them into one. The first thing that you see is A and B, and let's just say A is smaller than B. A is before B. So you output A, and then you move on to the next record. So you are comparing D and B, and between B and D, B is smaller, so you output B, and then you move on to the next one. So you have D and C is smaller, so you output C, and then you move on to the next item. And you have D and E, and you pick D, and you repeat this process, and as a result, you are going to have a totally sorted run. Okay? So I think it is fairly intuitive, right? Fairly intuitive. In this example, I'm showing that I'm merging 2 runs into one run. But in some cases, yeah, it is possible to merge like 4 runs into one run, 5 runs into one run, or 100 runs into one run. This is a configurable parameter, okay? So let's talk about more details about that. So let's consider a general case. So you have run 0, run 1, run 2, run 3. And let's just say you have 1 gigabyte of main memory. Okay, 1 gigabyte of main memory. And let's say you decide to merge 2 runs into one run. Let's just think about this scenario, okay? What you typically do is you have 1 gigabyte of main memory, and what you do is you split this 1 gigabyte into 3 pieces, okay? So you prepare 3 buffers when you are merging. 1 buffer for R0, another buffer for R1, and another buffer for the output run. And let me name this R0 prime. So 1/3 of 1 gigabyte, 1/3 of 1/3 of the gigabyte, so 1/3 gigabyte as well. And what's going on is, let's just say R0 is fairly big, like 1 gigabyte inside. So you cannot fully load the data into this like relatively small buffer. So what you do is you keep reading the data from R0, and once the dedicated buffer is full, then you stop, okay? And then you move on to R1, and you, from the beginning, you keep reading the data and loading the data into the buffer, which is 1/3 gigabyte at this point. And then, given these things, you compare the records, and those records are in the main memory, so you can quickly see them, right? I mean, you can quickly access those because everything is in the main, those records are only in the main memory. So you can compare those records and then you can start outputting those records in the buffer that is dedicated for this output run. So what you see here is there can be one disk seek, okay, for 1/3 of the gigabyte that you read from R0, and only one disk seek is needed for R1, and one disk seek is needed for the output run to handle this much data. So for each run, you can have one disk seek, like almost one disk seek for this much data. So this technique is called the buffering. And why do we ever need buffering in practice in general? Okay. So let me actually ask you a question. Do you understand why I'm trying to do buffering here? What's the main purpose of buffering in general in data management? I'm trying to reduce the number of something on disk. What is that? As the buffer size increases, I'm going to reduce the number of this operation. Yes, David, that's correct. So what's going on is only with one disk seek, I can read, right, 1/3 gigabyte of data with one disk seek. If I don't use buffering, in this case, for example, I read one record, I read one record, and then I write one record. So without buffering, for every record, I need to access the disk for every record, which means I can handle about 100 records per second because each disk seek will require about 10 milliseconds. So the system will be extremely slow. So how can we reduce the number of disk seeks? The key idea is one single word, buffering, okay? So if you have some interview question, oh yeah, so I'm designing a storage system and how unfortunately it's very slow, and I suspect that that is because there are too many disk seeks. Then what is the word that you need to pick? Yeah, let's use buffering, okay? So when you merge two records, two runs into one run, then in the main memory, you need to split the 1 gigabyte disk space for two buffers, B1 and B2, and then one single buffer for output purposes. So you are going to have relatively big buffers, okay? So when you merge two runs into one run, then in terms of, so you will reduce the number of disk seeks because every buffer will be big. So that's a good thing. The downside is you are merging two runs into one run. So you are unlike to merge all of the runs into one single run. So you are going to have more and more merging passes. So the number of passes will increase, okay? So as you have larger buffers, or as you merge fewer runs into one single run, then fewer disk seeks, more passes. What do you mean by more passes? So in each pass, what you need is every record will be read once and then written once. So more passes means more block transfers, more blocks that you need to read or write, because in each pass or phase, each record will be read once and then written once, okay? So if I decide to merge 4 runs into one run, then let's think about this case. If I'm merging R0, R1, R2, R3 into one single run R0 prime, then I need, how many buffers do I need in this case? I'm looking for a number. Would you type the number? How many buffers do I need in this 1 gigabyte of memory space? How many buffers do I need? I want to merge 4 runs into one single run. Yes, Gabriel, that's correct. So R0, R1, R2, R3, for these 4 input files, I'm going to have 0.2 gig buffer, okay? And then I will need 0.2 buffer for the output purposes. And typically, the wisdom is to evenly distribute the available memory. The reason is, if one of the files is received a lot smaller space than others, then there'll be more disk-6 happening there. So it's like the worst guy screwing up everything. So you need to do something as a team. And unfortunately, in this case, the performance of the team is determined by the straggler, the slowest member, or the weakest member. Therefore, evenly balancing the resources is a key idea. And this is actually a very important key principle in many computer science problems. Why equal distribution is good? Because in many cases, the performance is determined by the straggler. So I'm not sure if you guys have heard about systems like MapReduce. What is the key issue in MapReduce, which is a highly parallelizable data processing system? It's all about helping the straggler. So when many members are working together, and if the goal is to wait until all of the members are done, then the overall performance is affected by the stragglers, the slowest members. So MapReduce systems have some support for helping stragglers or dealing with the stragglers, okay? So it's similar. So why evenly distribute the memory because that's better, okay, at a very high level. And in this case, let's just see what's going on. So previously, I tried to merge 2 runs at a time. This time, I'm trying to merge 4 runs at a time. What it means is, if we are merging more runs into one, then number of passes will decrease, okay? Because if you merge all of those runs into one single run, then you need only 1 merge pass. That's a good thing, okay? As you merge more runs into 1 run, you will have fewer passes. You will read and write less block transfers. However, the downside is, what's the downside? If we decide to merge too many runs at a time, we will do some operation too much, too frequently. What is that operation? Would you type? I worry that I will do some operation too often if I'm merging too many runs. It starts with S. What is that operation? That is disk-seek. Because when you merge too many runs, then you are going to have you need more and more buffers. But the main memory is limited. Therefore, each buffer will be getting smaller, and therefore we are going to have more and more disk-seeks. So the point that I'm trying to make is, and also in homework assignment 3, there will be a question that will help you understand this balance. You must not merge too many runs at a time or too few runs at a time, because you will be doing too many passes or you will be doing too many disk-seeks. So there is a good balance, okay? Not too many, but not too few. It's just analogous to the importance of balanced life, right? Your life needs to be balanced, and it's very, very similar, okay? So this is the high-level overview of external sorting, and the slides show some detailed algorithms, and I will let you know after I post the 3rd homework assignment. So there are lots of things that I need to do, like creating programming assignment 1, midterm exam, posting, and thinking about programming assignment 2. But I think I will do a survey Tuesday next week, and definitely posting homework assignment 3. And if you look at the slides, there'll be more details about this, and there'll be some formulas about like how many disk seeks we are going to have and how many passes we are going to have. And my recommendation for you is not to memorize those formulas. Okay, it's too much. And I don't think you will keep memorizing those formulas like for the next 20 years, right? Is it going to be the case? 20 years from now, without thinking about this at all for 20 years, can you recover this formula in your head? Probably unlikely. Then it's dead knowledge. So what I want is you should be able to derive the number of disk seeks and number of block transfers. And we'll try to do this one more time next week, okay? But that's what I want. And once you possess that ability, then you don't have to memorize formulas. And given different assumptions, you will still be able to get some good answer. You'll be able to estimate the cost. So again, in this is an example and of doing some operation, and you need to understand the importance of two things: understanding the algorithm. So like, can you, given an example, can you do this? Can you develop a running example given some situation? Number two, can you estimate the time, how long it will take? And because we will be given the per unit cost for disk seek and block transfer. Transfer means reading or updating, okay? Block transfers. What you really need is how many disk seeks am I going to have and how many block transfers am I going to have? That's the key thing, okay? Then you don't have to memorize the formula. And if you blindly use these formulas, then you may actually get the wrong answer because there are certain assumptions and it may not be true, okay? So we have about 10 minutes or so. Let's try to so, well, I will go over this example next time, okay? So one thing is like merging. And the next one is join. And this is extremely important. So sorting is important, but join is also very important in the sense that, as we will study later, a good database design is not to put everything into a single table, okay? In particular, information about instructors and data about departments must not be put together inside a single table. Then you are going to have some redundancy, right? In general, there is a many-to-many or one-to-many relationship. So let's just say instructor 1, instructor 2 are both in computer science. And all of the information about computer science will be repeated in the table. That's what we learned early, and we are going to learn some theory behind this a couple of weeks later. So we need to split the data into multiple tables. In general, one table for instructors and one table for departments. And if there are many-to-many relationship between instructors and departments, then we need a third table, okay? Because there might be like 10 instructors and 10 departments, but there could be up to like 100 relationships between instructors and departments. So we need a third table. So my point is, we have to have many tables in general or multiple tables to avoid redundancy. However, in many cases, the data that we need are not necessarily in a single table. The data that we need to process may be spread over multiple tables. Therefore, we need to do join operation. Mostly natural join, okay? Natural join means like equality involved, and we naturally consider common attributes, actually all of the common attributes. Natural joins are very, very often. Of course, there are more general joins that we covered called the theta join, where this theta is a predicate that can be anything, like equality or inequality or any other complicated operations. So given such join operations, we are going to learn 5 different algorithms, and unfortunately, they are relatively slow. So what it means is joins are very frequently used, but they're also very expensive because you need to combine or you need to correlate data from multiple sources. So important, but costly. Frequently needed, but inherently expensive. So researchers have been, like so many smart people have been studying many different join algorithms. We will learn like 5 classical algorithms, but hundreds or thousands of join algorithms that have been developed for different cases, like single database systems, distributed parallel database systems, or other like data analytic systems, lots of different join algorithms because we had to combine data from multiple sources. So there are commonalities. So you need to understand every join algorithm, and you need to be able to estimate the cost for each algorithm, okay? So for each of those 5, and we also learned external sorting for each algorithm, you need to understand how it works and you need to estimate the cost. And what matters is the number of disk seeks and the number of block transfers, okay? So let's start with the first and easiest to join algorithm. And this one is nothing fancy. This is the like most dumb idea of doing a join operation. So it is just following the the definition of join, like conceptual meaning of join. You have 2 relations, R and S, and you iterate over every record in R, okay? Every record in R. And for every record in R, you do a full scan on S, and then you check if the join condition theta is satisfied. And if the join condition is satisfied, then you put the records together and then you output it. So that's the concept of nested loop join. 2 for loops, okay? So for every record in R, you do a full scan on S and you find all of the matches, and then output, for each matching case, you output the concatenation of the matching records. And here, because you have 2 for loops, R is called the outer relation and S is called the inner relation because R is in the outer loop and S is in the inner loop, okay? Outer, inner. So let's look at this example and let's try to understand what is going on. So in this example, I have 6 records in relation R, okay? 1, 2, 3, 4, 5, 6 records in R, and in S, 4 records in S. And I also assume that this is a way simplified example. There are 3 blocks, okay? So 3 blocks and total of 6 records, okay? And which means 2 records per block. So what happens is, for this record, you do a full scan on S. And then you move on to the next record and you do a full scan on S. So first, let's try to understand the number of block transfers, okay? Here, I read the first block, this one. That's the minimum IO unit. So I read the first block, meaning that I read the first 2 records. And this is the minimal unit, and I can keep it in the main memory. Okay, I can keep it in the main memory, just 4 kilobytes of data. And I do a full scan on S, and let's just say S is fairly large, like 1 terabyte in size. So what happens is I keep these 2 records, and then for the first record, I do a full scan on S. So I read 1 terabyte of data. And block transfers, 1 block read, and then every block in S will be read. So in this example, this is a weird example because I'm saying that 2 blocks occupy 1 terabyte of space. It's a little weird, but just assume that 1 full scan on S while reading every block in S once. So here, block transfer number 1, block transfer number 2, block transfer number 3. And then I move on to the next record and I need to do a full scan on S. So like for every record in R, we do a full scan on S. And because S is too big to fit into main memory, so nothing can be fully loaded in the memory. So you need to read everything from scratch. So block transfer number 4 and block transfer number 5. So again, one block transfer to read the first 2 records or the first block in R. And for the first record, one full scan on S. For the second record, one full scan on S again. And every record, every block in S needs to be read from scratch for each record in R, okay? And now we completely process the first block in R and we move on to the next block, okay? So we read the next block, so that's the block transfer number 6. And for this record, we do a full scan on S. Therefore, we will do additional block transfers. Every block in S will be read once from scratch. And we are done, and then we move on to the next record in R without any block transfer because this one is kept in the main memory. And we need to do a full scan on S. Therefore, I don't have like more steps. But you need to do a full scan on this, and then you are going to have block transfer number 9 and block transfer number 10 and so forth. So at a very high level, for each record, a full scan on S. If S is 1 terabyte in size, and if there are 1 million records here, it needs to be 1 million, then you will see that 1 terabyte of data read 1 million times. That is like 1 million hours or longer. And it's going to be a very big number. I don't know how big that is. So that's the high level understanding of the nested loop join. And unfortunately, it's a 120. So let's stop now. And please participate in the survey. When we meet next time, I hope I will be able to cover merge sort again, the XML sorting, and